Section 5.5 Calorimetry. The value of delta H can be determined experimentally by measuring the heat flow accompanying a reaction at constant pressure. Typically, we can determine the magnitude of the heat flow by measuring the magnitude of the temperature change the heat flow produces. The measurement of heat flow is calorimetry. A device used to measure heat flow is a calorimeter. Section 1. Heat capacity and specific heat. The more heat an object gains, the hotter it gets. All substances change temperature when they're heated, but the magnitude of the temperature change produced by a given quantity of heat varies from substance to substance. The temperature change experienced by an object when it absorbs a certain amount of heat is determined by its heat capacity. C. The heat capacity of an object is the amount of heat required to raise its temperature by 1 Kelvin or Celsius. The greater the heat capacity, the greater the heat required to produce a given increase in temperature. For pure substances, the heat capacity is usually given for a specified amount of the substance. The heat capacity of 1 mole of a substance is called its molar heat capacity, C sub m. The heat capacity of 1 gram of a substance is called its specific heat capacity, or merely its specific heat. The specific heat, C of S, of a substance can be determined experimentally by measuring the temperature change that a known mass m of the substance undergoes when it gains or loses a specific quantity of heat, Q. Specific heat is the quantity of heat transferred divided by the product of the grams of a substance times its temperature change. For example, 209 joules is required to increase the temperature of 50 grams of water by 1 Kelvin. Thus, the specific heat of water is 209 divided by 50 divided by 1 equals 4.18 joules per gram Kelvin. The temperature change in kelvins is equal to magnitude of the temperature change in degrees Celsius. Delta T equals K delta T in degrees Celsius. When the sample gains heat, positive Q, the temperature of the sample increases, positive delta T. Rearranging equation 521, we get Q equals the specific heat times mass in grams times the change in temperature. Thus, we can calculate the quantity of heat that a substance has gained or lost by using its specific heat together with its measured mass and temperature change. The specific heats of several substances are listed in Table 5.2. Notice that the specific heat of liquid water is higher than those of other substances listed. For example, it's about 5 times as great as that of aluminum metal. The specific heat of water affects Earth's climate because it makes the temperatures of the oceans relatively resistant to change. It's also very important in maintaining a constant temperature in our bodies, as we'll discuss in the Chemistry of Life box later in this chapter. Section 2. Constant pressure calorimetry. The techniques and equipment employed in calorimetry depend on the nature of the process being studied. For many reactions, such as those occurring in solution, it's easy to control pressure so that delta H is measured directly. Recall that delta H equals heat. Although the calorimeter is used for highly accurate work or precision instruments, a very simple coffee cup calorimeter, as shown in Figure 517, is often used in general chemistry labs to illustrate the principles of calorimetry. Because the calorimeter is not sealed, the reaction occurs under essentially constant pressure of the atmosphere. In this case, there is no physical boundary between the system and the surroundings. The reactants and the products of the reaction are the system, and the water in which they dissolve as well as the calorimeter is part of the surroundings. If we assume that the calorimeter perfectly prevents the gain or loss of heat from the solution, the heat gained by the solution must be produced by the chemical reaction under study. In other words, the heat produced by the reaction, Q sub reaction, is entirely absorbed by the solution. It doesn't escape the calorimeter. We also assume that the calorimeter itself doesn't absorb heat. In the case of the coffee cup calorimeter, This is a reasonable approximation because the calorimeter has a very low thermal conductivity and heat capacity. For an exothermic reaction, heat is lost by the reaction and gained by the solution, so the temperature of the solution rises. The opposite occurs for an endothermic reaction. The heat gained by the solution, heat of solution, is therefore equal in magnitude to heat of reaction, but opposite in sign. The heat of solution is equal to negative the heat of reaction. The value of the heat of solution is readily calculated from the mass of the solution, its specific heat, and the temperature change. The heat of the solution is the specific heat of the solution times the grams of solution times delta T equals negative heat of reaction. For dilute aqueous solutions, the specific heat of the solution will approximate the same as that of water, 4.18 joules per gram Kelvin. Equation 523 makes it possible to calculate the heat of reaction, or Q of reaction, from the temperature change of the solution in which the reaction occurs. A temperature increase, delta T is greater than 0, means that the reaction is exothermic. The heat of reaction is less than 0. Bomb calorimetry. Constant volume calorimetry. One of the most important types of reactions studied using calorimetry is combustion, in which a compound, usually an organic compound, reacts completely with excess oxygen. Combustion reactions are most conveniently studied using a bomb calorimeter, a device shown schematically in Figure 518. The substance being studied is placed in a small cup within a sealed vessel called a bomb. The bomb, which is designed to withstand high pressures, has an inlet valve for adding oxygen and electrical current to initiate a combustion. After the sample has been placed in the bomb is sealed and pressurized with oxygen. It's then placed in the calorimeter, which is essentially an insulated container, and covered with an accurately measured quantity of water. When all the components within the calorimeter have come to the same temperature, the combustion reaction is initiated by passing an electrical current through the fine wire that is in contact with the sample. When the wire becomes sufficiently hot, the sample ignites. Heat is released when combustion occurs. This heat is absorbed by the calorimeter contents, causing a rise in the temperature of the water. The temperature of the water is very carefully measured before reaction and then after reaction when the contents of the calorimeter have again arrived at a common temperature. To calculate the heat of a combustion from the measured temperature increase in the bomb calorimeter, we must know the total heat capacity of the calorimeter, C sub cal. This quantity is determined by combusting a sample that releases a known quantity of heat and measuring the resulting temperature change. For example, the combustion of exactly 1 gram of benzoic acid in a bomb calorimeter produces 26.38 kilojoules of heat. Suppose 1 gram of benzoic acid is combusted in a calorimeter and it increases the temperature by 4.857 degrees Celsius. The heat capacity of the calorimeter is then given by C sub cal is 26.38 kilojoules divided by 4.85 degrees Celsius equals 5.431 kilojoules per degree Celsius. Once we know the value of C sub cal, we can measure temperature changes produced by other reactions. From these we can calculate the heat evolved in the reaction, Q of reaction. Q of reaction is negative C of cal times the delta T. Because the reactions in a bomb calorimeter are carried out under constant volume conditions, the heat transfer corresponds to the change in internal energy, delta E, rather than the change in enthalpy, delta H. For most reactions, however, the difference between delta E and delta H are very small. For the reaction discussed in sample exercise 5.7, for example, the difference between delta E and delta H is only 1 kilojoule per mole, a difference of less than 0.1%. It's possible to correct the measured heat changes to obtain delta H values, and these form the basis from the tables of enthalpy change that we'll see in the following sections. However, we need not concern ourselves with how these small corrections are made.